Okay, let's start the sixth part. Canadian chops production practice 6.1 Initial and sustained sand influx. To initiate sand influx, the following completion practice are usually followed in chops wells development. A large diameter, about 20 meters millimeters perforation ports are used. Perforation spacing of 26 or 39 shots per meter. More rarely, closer spacing is used, and under balanced perforation is better than over balance. In thin formation, below 6 meters, the entire height is perforated. In thicker formation, 6 to 8 meters of perforations are placed towards the bottom of the pay interval. More rarely, these are placed in the zone of highest production potential. Perforations are fully fixed, regardless of the wear inclination or orientation. Chops wells range from 0 to 45-degree inclination. Steeper inclinations are not advised. The progressing cavity PC pump is placed within the inlet, the bottom of the 0.5-meter long T-pipe, 1 to 2 meters below the lowermost perforation. A well-reservoir compatible fluid is being placed into the annual initially keeping it full. The PC pump is started and brought up to a speed and allowed sand and oil production to be sustained 50 to 100 rpm usually, depending on sand cut. The annulus fluid addition is assisted or dismissed slowly so that the annulus fluid level drops where the pump is operating at full capacity. This generally initiates and maintains sand influx. If sand influx does not occur, a series of steps is undertaken to perturb the formation and remove it where the PC pump is in the hole. Such steps may include aggressive injection of lighter battery oil into the annulus at a high rate, rapid injection of 5 to 10 meters of heated compatible oil through the annulus, simulations injection through the tubing and the annulus once the rotor is backed out of the stator. If attempts and sand initial failed, the pump is withdrawn from the hole and the chamfer, a small rocket propellant charge, ignites downhole. Pressure passing or some other workover method is carried out. In general, about 85 to 90% of chops wells come on to production without having to withdraw the pump, and even with the best of techniques, about 5% of wells never successfully achieve sand co-production. Sustaining sand influx is necessary to produce heavy oil at economic rates. If a mechanical failure or a variable or pump blockage by sand occurs, a workover is required. Tubular goods are withdrawn, and before reinstallation, the wire thoroughly cleaned of sand using a mechanical baler, a pump to surface truck, a jump pump, foam treatment, or other techniques. Production is returned after pump reinstallation. However, the loss of sand influx may arise because of a number of processes that take place outside the casing. The perforations may be plugged with sand arches, cement fragments, concretions, or fragments of shells. Sand may have become replaced around the wire in a dense state so that the gradients available are no longer sufficient to destabilize the sand. The wire may have become disconnected from the far-field source of pressure, and insufficient flow velocities existed to allow sand flow. The overburden may be supported sufficiently by the stable interval regions so that the component of the choke drive mechanism is no longer available. The reservoir may have reached a depletion state so advanced that the necessary pressure gradients to sustain sand influx are no longer possible. In this case, various injection approach may be used with the pump in the hole, a rotor in stator, or rotor backed out. Or the pump may be withdrawn and a full workover implemented. It appears that methods that achieves the largest perturbation of the variable environmental and are the most effective and re-establishing sand influx. 6.2 Lifting approaches. 6.2.1 Reciprocating pump and related device. Since the 1930s, Husky Oil Company and a number of small oil companies have produced heavy oil in the area using a reciprocating pump with bottom hole ball valve pumps driven through suction rods from the surface with a pump jack. These wells generally produced 3 to 7 barrels per day, with a maximum productivity of perhaps 10 to 12 barrels per day. In ideal circumstances, in almost all cases, the maximum production rate of the wells was limited by the maximum rod for velocity. The problem of rod. The problem of rod for velocity is directly related to the viscosity of the fluid in the production tubing. This fluid generates drag on the sucker rods as they fall, and a retarded pump rechange rate is also generated because The viscous oil must flow through the pump body to recharge the pump cavity of the downstroke. If largely pure 10,000 cp oil is being produced with a small amount of sand and less than 5% water cut, as the pump jack moves on its downward stroke. The rod cannot fall any faster than about 0.15 to 0.25 meters per second. This gives a reciprocation rate of about 3 to 5 strokes per minute, depending on the pump configuration, giving a production capacity of less than 10 barrels per day. Furthermore, the upstroke requires much more energy than in conventional oil because of the viscous drag on the rod and the generally low annular pressure. Given the typical displacement volume in a reciprocating pump designed for a 7-inch casing, and given the fact that the produced fluid often develop fume and the inlet to the pump, thereby reducing its efficiency. The maximum production rate is generally limited to 7 to 10 barrels per day of fluid. In the case of a well that is divided at angles above 20 degrees, the problem of slow rod fall is even more severe and steel erosion more seriously. Is it possible to push down the sucker rod at the surface? The answer is no. This gives little to no advantage because the rod spiral in the hole and fall to place a downward force on the pump at hole bottom. Various patented and field-rigged methods were tried over the years to overcome the problem of low road fall velocity through some form of spring or energy recharge device at the hole bottom, and could pull the pump plug and the rod string back down at a faster velocity, allowing increased pump speed. Apparently, none of these methods proved to be sufficiently effective to warrant adoption in the Canadian oil industry, and at present there are no known applications of such device. Several different techniques to provide longer strokes or more uniform lifting power have been developed in horizontal thermal wells, where the elastomer of a PC pump may experience thermal breakdown. Standard reciprocating pump technology is used with no plastic or elastomeric parts. However, several companies have concluded that lifting efficiency is correlated with the length of the stroke. in these horizontal wires. Two approaches have been developed for long-stroke pump: extremely large standard pump jacks, often set at an angle for deviated wires, are used at deviated wires are used at the One-Flag project to provide a stroke length of 4 meters. These are being widely adopted elsewhere for similar projects such as SAGD implementations. Alternatively, the rotor flex system uses a large counterbalance belt on a tall frame that winds and unwind, giving a long stroke about 6 meters to a conventional bottom hole reciprocating pump apparatus. Apparatus driven by suck rods. In the 1980s in Canada, several hundred high-efficiency pump units were sold. This device used a small hydraulic power source, hydraulic lift, and gas pressure accumulator to store part of the energy on the downstroke of the drive rod in the tubing. The unit used electronic control methods on the stroke limits and could be almost infinitely programmed in terms of stroke length and speed. Claims of greater energy efficiency, notwithstanding this device, were gradually abandoned. By the later half of the 1990s, no HEP units were operating in the heavy oil industry in Canada. In large part, the HEP systems were displaced by the rapid development of PC pump technology during 1982 to 1995. 6.2.2 Continuous sand extraction CSE pump. The device developed in this for pumping packed sand of 35 to 50% porosity from wells was developed in the 1990s. The continuous sand extraction pump is a 3-meter stroke piston pump lowered on the bottom of tubing. It is used as an alternative to a mechanical baler and other device to clean sand from the hole, or to cope with periods of extremely high sand influx with no free gas in the incoming fluid, where even a PC pump will have difficulties reciprocating the tubing across the CSE pump cylinder and piston at hole bottom so that a sink slurry or even solid sand can be drawn up into the body of the pump, where the dense sand in the tubing above the pump is displaced upward. Continued stroking of the CSE pump results in a large column of sand, and in cases where there is a higher annular fluid level so that delta P is not excessive, The sand can be directly pumped to surface. If the sand cannot be pumped to surface easily, it is also possible to feed viscous oil into the annulus to promote the dilution of the sand in the wellbore and allow easier inflow to the CSE pump. If no fluid is trickled into the annulus, the CSE pump will draw down the annular lever until the delta P between the wellbore and the formation is large, and this promotes sand influx. Typically, a CSE unit will be used for the period of troposphere when the sand content is high, so that a PC pump will not have to contend with sand concentrations combined with the possibility of steel fragments of perforation charge fragments that could damage the elastomer. Once the sand content drops below about 10%, the low capacity CSE pump can be replaced with a higher capacity PC pump. 6.2.3 Jet pump development and use. Canada Petroleum has carried out research into jet pump lifting systems for a decade. Jet pumps have been tried repeatedly in Canada and are widely used in one form or another for hull cleaning functions, powered by a pump-to-surface unit or similar high-rate pump system. However, they have never found use in troposphere production as a long-term lifting system. The reason for this have never been made public, but it can be speculated that the problem of lifting capacity, internal erosion of the steel in the jet impingement area, and the generator of difficult emulsions were responsible. In the absence of published data, it is difficult to say precisely which was the most important issue that caused jet pump technology to fail, but there are some logical suppositions that are worthy of comment. In particular, developing tropes were production schemes to have advantage of large fluid rate increases that accompany sand ingress means that the production engineer must design operations to cope with high early sand influx, perhaps as high as 15 to 20% of the total fluid volumes entering the pump in later depths. The early high sand content conditions are triggered and maintained by aggressive drawdown of the annular fluid, so that a large delta P between the wellbore and the reservoir is required. Aggressive drawdown also means that the gas content in the form of foam and at the whole bottom in the fluid flowing to the pump intake can be large. If there are low pressure in the jet orifice region, this gas can expand suddenly, reducing pump efficiency. In the case of a jet pump, a large drawdown increases the energy requirements substantially, and high liquid jet velocities are needed to achieve lifting capacity of 10 to 30 meters per day of reservoir fluid against the fluid height difference as large as 600 meters in wells that are 650 to 700 meters deep. This lifting requires maintenance of a delta-P of about 5.5 to 6 MPa, and it cannot be done with jetting viscous oil through the pump, nor is it economical to use diluent. Therefore, water must be used as a jetting agent. The water carrying the motive power has to be free of abrasive solid because it passes through a small constrictive nozzle at the tip of the jet to build velocity. This means that it is difficult to economically recycle water separate from the fluid production stream between the water becomes contaminated with clays and silt, leading to rigorous filtration requirements at the surface for water recycling. The shear energy required to accelerate the variable fluid so that lifting can occur requires high water uh, velocity and reasonable water rates. Once the water has left the jet nozzle, it can entrain sand and abrade the outer body of the jet jump. Adding water reduces the viscosity of the fluid and therefore reduces the damping effect and the high viscosity has on the momentum transfer responsible for abrasion. To keep abrasion to a minimum, it is best to keep viscosity as high as possible and the velocity as low as possible. Jet pump fails on both counts. Along with the clay minerals and polar molecules in the heavy oil, the high shear rate of a jet pump also is ideal for the generation of emulsions. Furthermore, many software produce reservoir fluid with less than 10% water for many years, and much of this water separates easily at the surface in the heated stock tank. With a jet pump, the motive power must be water, and the addition of substantial amounts of water inhaled by the jet pump leads to additional separate difficulties and cost at the surface. 6.3 Progressing cavity pumps. 6.3.1 Evolution of PC pump used in Canadian heavy oil. In the 1920s, a French university professor developed a concept of an eccentric helical rotor turning in an external stator, also with a helical hull, but actually consisting of two helices together. If the elastomer in the stator has an interference fit with the smooth surface of the rotor. A series of fully isolate cavities progress along the length of the rotor-stator system. The pump operators. The contrast to a screw, the pump developed by Professor moves fluid fully isolated cavities in any direction, even downward. The concept is used for mud motors that rotate the drill bit at the bottom of the hole during drilling, particularly in highly deviated and horizontal wells, because the seals cavities progress along the pump body between the stator and the rotor. The term progressive cavity pump or PC pump is used. Módulo company in the UK developed and marketed the PC pump for years on the basis of the original patent, gradually improving them. Initially, pumps were plugged by inadequate elastomer quality, giving short life in several usage conditions. Elastomer deterioration in the presence of polyaromatic compounds leads to insufficient seal at contact point to give high rates at reasonable depth value across the pump. Better elastomers developed in the 1970s rigorous quality control in the injection molding of the stators, precision welding of stator sections, and elimination of heat damage to elastomers result in improved pump quality and capability. The first PC pumps in high V oil were tried in California in the 1960s and 70s. In cases where where sand content was extremely small, they were introduced to the Canada HOB in the early 1980s. These early designs had short lifespans, and there was little confidence in their ability to operate under the demanding conditions of sand influx, particularly with large sand cuts and at the beginning of production. Nevertheless, based on some experience where pumps lasted reasonable well, and also because they overcame the rate limitation associated with slow road fall in reciprocating pumps. PC pumps continued to be tried by various small operating companies. The most important factor was that these pumps often could double and triple their production rates, and even though modern of heavy oil was slim. This greatly affected profitability. Continued development work and improved quality control on the stator molding result in gradually improving quality, capacities, and lifespans for PC pump. For example, of several original world manufacturing sets of the injection mold stators. The quality and lifespan of the stator varied considerable, and this caused difficulties such as premature elastomer wrapping or embrittlement. Competition has led to improvement in the products of all PC pumps companies. But there are some manufacturers in China and elsewhere that still have poor track records. In general, the problems include poor quality control and chemical incompatibility with the fluid being pumped. Currently, better quality control and more manufacturing sites around the world continue to improve the performance and lifespan of PC pumps. A decade after the first introduction in Canada in 1982, PC pumps became widely accepted as the standard for topsoil. They are now available for a wide range of capacities for many different conditions. PC pump with capacities as large as 1,000 meters per day within 2,500 meters lift capacities are available for convenience light oil. For lifting of gassy heavy oil and sand slurry, pump life has been extended from 6 to 8 months to 15 to 20 months, and a wide variety of capacity and size are available. For chops applications, the maximum volumetric rates are 70 meters per day per 100 mpm, and the delta-P lift capacity tend to be approximately 800 to 1,200 meters, with lower capacities for shallow wells. There are a number of independent companies providing PC pumps, but many of them purchase their components from the same suppliers who have perfected the method of high quality stators elastomers injection. The two largest companies in Canada were Redfoo and Kudu Pumps. But other suppliers are providing PC pumps for heavy oil wells in addition to specialized devices such as surface transfer pumps for slurries and viscous oil. 6.3.2 Current PC pump practice in the HOB. Since the early 1990s, new chops were coming onto production in the HOB not only use PC pumps almost exclusively, but also used only those developed in the area, as these are designed to provide the necessary resistance to sand in the fluid. If a workover is done on an old chops wells uh, to increase productivity. Usually, the reciprocating pump is removed and the PC pump installed. A relatively standard configuration for new chops well is a PC pump 6 to 10 meters long with a DP capacity of 1,000 meters of differential lift, designed at a stator rotor pitch to give a production rate of between 10 and 50 barrels per 100 rpm. The details as to the pitch, eccentricity, and other design parameters depend on the expectations of producing company and various wear factors such as viscosity, expected annular fluid level drawdown, gas content, and so on. Many companies use a software program developed by the Canadian Centre for Frontier Engineering Research to allow easy choice of the optimum PC pump for particular applications. The advantages of PC pumps for heavy oil lifting in trough-wear configuration are the following: a PC pump can lift the high viscosity fluid with large solid concentration and they are produced during trough ignition. Sand cuts up to 45 to 50% of the dead fluid can be left. The PC configuration can operate under conditions of substitutions gas volume as long as the gas in the form of fume and not as large gas slugs. A PC pump has low internal fluid shear rate because the pump physically lifts the fluid in each cavity. This low shear rate limited fluid problems. The low fluid velocities in the PC pump means that steel erosion is not an issue, although some abrasion of the rotor invariably takes place. There are no values to clog or gas lock, as in some other types of pumps. In general, a PC pump has a relatively low capital cost and power cost. The low wellhead profile associated with the rotary drive unit, particularly the new hydraulic drive units, gives less visual disturbance or clutter and at multiple wear pads and allows more effective placement of wears, a smaller surface footprint for multiple wear pads, and greater ease in maintenance and changeouts. There are some disadvantages that must be kept in mind when operating PC pump in chops wear. A rapid failure rate occurs if the pump is allowed to run dry. This may arise because of excessive annular fluid drawdown or because a large gas cap generates a prolonged gas slump, and there is a tendency for elastomer wrapping if pebble or a piece of metal enters the pump. A number of recent developments in PC pump design have been triggered by the unique demand of the Canadian heavy oil industry and chops approaches, and this should be mentioned. 6.3.3 Sloppy feed PC pumps. PC pump efficiency is determined with water pump tests in the factory using manufacturer's criteria. In the early 1990s, it was recognized that PC pumps retained a high efficiency, above 80%, for pumping viscous heavy oil despite substantial rotor wear from sand abrasion and destroyed the interference fit. When one pump was tested with pure water, efficiency of only 10 to 30% were found because of fluid slip between the rotor and the stator. Now, PC pump manufacturers often sloppy feed pumps for chops applications, recognizing that using a tight feed pump will result in abrasion of the leading edge of the rotors after a few months of use, leading to a sloppy feed in any case. An initial sloppy feed prolongs rotor life and permits rotors to be resurfaced and reused several times. 6.3.4 Charge pump conventional PC pump discharged all their fluid directly into the production tubing. PC charge pump have two sections. The lower one operates at a higher flow rate than the upper one at the same RPM because the rotor stator pitch is longer. Bypass ports in the stator at the junction of the two sections allow the excess fluid to be expelled into the annulus and provide charge fluid to the upper pump at a somewhat elevated pressure. Thus, delta P requirements across the upper pump are reduced and the gas bubbles in the produced fluid are particularly compressed. This increased the efficiency of upper PC pump stage. Also, the fluid that is bypassed apparently has some beneficial effects on variable performance. The part of the fluid back down the annulus across the perforations tend to the pump intake fluid, reducing changes of pump blockage by sudden sand slag influx, and perhaps reducing somewhat the negative effects of large gas slug. Also, blockage tendencies because of sand arcing in annulus between the pump stator and the casing are apparently reduced. 6.3.5 Constant elastomer thickness PC pumps. Difference heating of the stator elastomer during PC pump operation arises because because of different elemental elastomer thickness, leading to varying heating dissipation capacities along the stator body. If there is heating during pumping, this differential thickness leads to differential thermal expansion, which in turn leads to increased heating of the expanded sections, uh, exacerbating the problem, leading to elastomer deterioration and wrapping. To counteract this, the three-lobe stator PC pump was developed. This configuration provides an elastomer that has less thickness variation around the stator diameter, apparently in a number of service conditions. The three-lobe stator configuration also is a more efficient fluid lifter. However, it has not been widely adopted at the present time for chopsware. A helicoidal internal stator housing that reflects the helix-like curvature of the interior of the stator was introduced in 1998 to 1999. This design means that the elastomer can be pressure injected into the stator housing and achieve an almost constant thickness. This constant thickness virtually eliminates the problem of differential thermal expansion. This configuration comprises a small percentage of PC pumps, but some operators believe it helps prolong pump life in some fields and therefore adopting it more widely. Despite somewhat higher cost, 6.3.6 rotor wheel, the leading edges of the PC pump rotors are subjected to the greatest wear rate from sand abrasion to reduce the wear rate and maintain pump efficiency. The technique of bronzing the rotors was developed. In general, this can be expected to increase pump rotor life by 10 to 30%, perhaps more in the case of abrasive sand. It must be remembered that there are many reasons for pump breakdown other than rotor wear, and many PC pump rotors are changed routinely when a workover is performed. In addition to more resistant coating on the rotor, the advent of sloppy feed PC pump has reduced the rate of rotor wear and the frequency of rotor replacement. Downhole drives for PC pumps. Downhole drive approaches to PC pump operation are intended to replace the surface rod driven method that is the currently industrial standard. Electrical and hydraulic downhole drive PC pump approaches have been pursued for over a decade. There are currently approximately 50 to 100 of each of these types of pumps operating worldwide to produce heavy oil. but not with the high sound cut typical of Canadian production from chopped wires. The electric PC pumps is available through several companies. Baker Hughes in tech is one of the largest suppliers. It has not had a good record of durability, and the units are expensive compared to rod-driven PC pumps. Several attempts have been made to install these pumps in Albert chops wires, but ESPCP devices do not cope well with large quantities of sand. The research arm of Venezuela National Petroleum Company, Petróleo, has had an active research and development program for some years into ESPCP use in heavy oils, and monitoring the progress of this and related activity is worthwhile. The hydraulic PC pump is newer than the ESPCP, and there is little track record yet for this durability. The HSPCP requires two hydraulic lines from the surface to the drive unit above the pump in addition to the usual crude oil production tubing. As a result, installation and the servicing are more expensive. Development of a PC pump that is driven by rotation of the tubing string itself, without a drive rod string inside the tubing, using a bearing attachment joint between the PC pump stator and the tubing to drive the rotor, has been tried and may still under development at this time. The advantages of such a system are simpler workovers, as only the tubing and the pump have to be withdrawn, saving a rod string trip. No internal impediments in the tubing in the upward flow of the oil sand slurry, thereby reducing flow resistance and eliminating sand induced wear between the casing and the drive rod. Direct installation of the PC pump pre-assemble with the rotor in place in the body is feasible, rather than introducing the rotor after stator echoing by carefully lowering the rod string until the stator bottom touches the tug bar in the bottom of tailpipe. However, rotating the tubing string means that the issue of wear between the casing and the tubing must be carefully addressed, because breaching the casing with rotating tubing is more seriously and much more expensive to rectify that tubing string breaching by drive rod abrasion. Of course, casing steel thickness is larger than tubing thickness, and there is no sand moving up the casing tubing annulus, as there is in the interior tubing rod annulus during conventional PC pump operation. Thus, wear rates should be low, and protective measures such as nylon wear sleeve installation can be undertaken to protect the casing and the tubing joints from wear. Alternatively, smaller diameter continuous tubing may be used instead of 3.5-inch tubing, avoiding the wear points associated with tubing colors. Both ESPCP and HSPCP technologies should eventually prove to be better for wears with high deviations or short radius turns, as the problem of rod wear of production tubing is limited. The development of hydraulic submersible drive PC pump is technology evolution area to monitor over the next 10 to 15 years to see whether the apparent benefits of downhole drive methods can bring greater economics and reliability to choke wear. Okay, let's see a video about the introduction of PC pump.
Hello, thank you for joining us. My name is Aaron Rennick, and I'll be your host today. CPEX is a progressing cavity pump manufacturer located in the great Midwestern state of Ohio. Our company was founded in 1973. Today, we are the largest PC pump company in North America, as well as a powerhouse in the global marketplace. More than a manufacturer, CPEX is a process solutions provider. I've had the pleasure of being a CPEX employee for 25 years. Today I'm a sales director for the company, but I have held positions in assembly, production, and engineering. In this presentation, my colleagues and I will demonstrate how does a progressing cavity pump work? What pump applications are PC pumps suitable for? What are the features and benefits and operating characteristics? The ease of maintenance of a PC pump, as well as covering the many reasons why to choose a progressing cavity pump. Now, I'll pass this on to Chris Brooks. Chris?
Hello, my name is Chris Brooks. I'm a territory sales manager for CPEX. I cover Georgia, Florida, Tennessee, North and South Carolina for the company. I've been associated with CPEX now for about 19 years, primarily in the sales role. I've got about 30 years experience in the pump industry overall. Today we're going to talk about progressive cavity pumps, or commonly referred to as PC pumps. A lot of good features and benefits from using a PC pump. And so we're going to talk about how they work, some of the applications you guys may see in water and wastewater, and then just some of the individual components and benefits. So what is a PC pump? How does it work? So it's a positive displacement pump. It actually is comprised of a pumping element that has two main components, a rotor and a stator. The rotor is the rotating portion of the pumping element. It's typically made out of a steel or a metal material. The stator is actually an elastomer. It's the stationary portion. It's made from elastomer, typically like a Buna or EPDM or Viton. Those two components go together. They actually form a cavity, and as the pump rotates, the cavity spirals from one end of the pumping element to the other. So you can say that cavity forms As the pump rotates, it spirals, it actually progresses down the length of the pumping element, which is why it's called a progressive cavity pump. There is a compression between that rotor and stator, and that does a couple of things. It helps form the cavity along a seal line and prevents a lot of slip or product from the high pressure discharge side back to the suction. So it kind of traps that cavity as it rotates. The cavity spirals from one end to the other, and the product comes out the discharge. Really, why are PC pumps used, or where are they used in water and wastewater? The two primary areas are chemical addition or chemical metering, and then sludge handling. There's not a lot of pumps available on the market today that can handle a wide range of products like that. So you can consider we do a lot of polymers, sodium hypochlorite or bleach, sodium hydroxide, caustic soda. So we do a lot of these thin metering chemicals, and then we also turn around and we do dewatered sludges, cake coming off a belt press. It could be 45% dry solid. So it's a pretty unique pump, and then it can handle such a wide range of material like that. Okay, the next area we wanted to talk about is maintaining progressive cavity pumps. A lot of people want to know, are these pumps difficult to repair in the field? They can be. Some of the larger pumps have extremely long stators, so they can be pretty heavy. Also, you have to allow for enough room on the discharge side of the pump to remove that stator off the end of the rotor. Many PC pump manufacturers now have a type of maintain in place component to their pumps, and this means you can actually go in, change the stator, sometimes the rotor or other components, without having to remove any piping whatsoever. That seems to be pretty common among most of the major manufacturers now. The maintain in place actually speeds up the maintenance time. So to change the stator, the times to do that are greatly reduced compared to a conventional stator. Because you don't have to remove any piping and have a spool piece on the discharge, the floor space requirements much less with the maintain in place designs. Some of the designs also include an adjustment on the fly. So basically you could go back, retension the compression between the rotor and stator as the stator begins to wear. So instead of having to run until you see a performance drop off, change the stator, you actually, when you see that performance change, you actually go in and retension that compression, and the pump's back to like new condition. What are the benefits of using a progressive cavity pump? Why would you use it instead of other technologies? One of the main concepts is the compression or the interference fit between the rotor and stator. This limits the slip or the product going from discharge, the high pressure side, back to suction. So it's a very efficient design. It actually is very repeatable and accurate. So we trap that liquid in the cavity, and once that cavity is full, we know what that volume is. So as the pump rotates, we're going to get a known volume per revolution. So by doing that, we can be very accurate in metering. We can also just by changing the speed of the pump, change the flow rate, even at very low increments. The PC pump is also a very low shear device. It doesn't put a lot of shear into the product, so liquids like polymer are very easily handled by a PC pump. Also, if you had a product that had solids that were brittle and you didn't want to break up, like yogurt with berries, for example, you could actually pump that without doing any damage to the berries. The pump can handle large solids. Some of the designs can handle solids as large as 4-inch. The pump can be self-priming. So if you had a below grade tank and you needed to pull liquid from below ground up into the pump, you could do that with a progressive cavity pump. They're very low net positive suction head requirements. So if you had a tank that had a very low level or a long section of suction line, you can actually use these pumps in those applications. We do single and multi-stage, so you can actually get very high pressures out of these pumps. They can also operate on very thin liquids as well as very high viscosity liquids. We pump everything from water or alcohol, which is very thin, up to dewatered sludge cake. Pumps can also operate in either direction. So the normal suction is coming in at a 90-degree angle to the pump. the discharge is out the end, we can actually reverse rotation to where the suction is coming in the straight component. A lot of times if we're pulling a suction lift, we will actually run the pump in that direction so the seal or packing is not in the suction casing. We can pull higher lifts in that configuration. So what are the typical operating parameters on the progressive cavity pump? The pumps have the ability to go from extremely low flow rates, like for metering small or dosing small amounts of chemical, down into the fraction of a gallon a minute range, all the way up over 2,000 gallons per minute. These pumps are commonly used on metering, where it's literally drops of fluid, and all the way up to large flow rates, up into the thousands of gallons a minute range. The pumps can also operate in a wide range of pressures, anywhere from 1 psi all the way up to over 700 psi. Viscosities, we can handle any kind of fluids from alcohol, water-like fluids, all the way up to dewatered sludge cakes, which can be over 1 million centipoise. The pump has the ability to operate in low temperatures down to like -4 degrees Fahrenheit, all the way up to about 350 degrees Fahrenheit. Our limitations on the temperature are the elastomers we use in the stator. Solids, these pumps have the ability to handle extremely large solids. We handle a lot of fluids that have a large percentage of solids, but are very small, all the way up to products that have large, in some cases over 3 to 4 inches size solids. The pump can also handle a mixture of air or gas and liquid as well as solids. So they're pretty unique in that way that they can handle not just liquid, but a mixture of those as well. We can also handle a large percentage of solids, all the way up to about 45% dry solids, which is like a dewatered cake in the wastewater industry. So what kind of flexibility do we have on the installation of these pumps? As we mentioned earlier, the pump can be rotated in either direction. So you can actually change the position of the suction and discharge on the pump if required. A lot of the pumps actually use a direct coupled method, so there's no belts, no couplings between the motor, gearbox, and pump. That eliminates any kind of alignment issues. The pump really doesn't care which position it's mounted in. It's pretty common for PC pump manufacturers to mount these pumps horizontally as a standard. But you also see a lot of these pumps mounted in the vertical configuration as well. Most pumps, the suction casing, since it comes in, the suction flange is at a 9-degree angle to the pump. That can typically be rotated at 90-degree increments and can be changed, that position, but can be changed as well. So again, the pumps are self-priming, so a lot of times you'll see these pumps pulling actually a high suction lift. Another component these pumps are used for is metering. They're very low pulsation and very accurate. So you can actually, when using these pumps on metering, you can actually eliminate the need for a pulsation dampener, like a lot of the other competitors do on metering. The pump doesn't use any kind of check valves. It actually acts as a valve itself, since there is a compression between the rotor and stator. As the cavity between the rotor and stator progresses out the length of the pump, as one cavity stops, another one's forming. And so it's almost an uninterrupted flow, so you see very minimal pulsations. Again, the pump can handle large solids, as we mentioned, over as high as 4 inches on some of the larger pumps. And because of the way the cavity is formed, when those solids are trapped in the cavity, you see very little damage from the pump. The pumps are used quite often on abrasive fluids. We pump everything from like a calcium carbonate slurry, lime slurry. Products that have quite a bit of solids in them. There is no restrictions once the product gets into the cavity. A lot of pumps have a check valve or some other restricted device in the pump. The PC pump doesn't have anything. Once the product enters the cavity stays the same shape from suction to discharge. We do limit speed when we're handling abrasive solids, just to try to prolong the life of the rotor and stator. And you can also, another method to reduce the abrasive wear on the pump is actually try to limit the slip. So a lot of times we'll do that by either reducing the discharge pressure on the pump or adding stages to the pump so we reduce that slip.
Thank you, Chris. Not all stators and rotors are created equal. Let's take a look at stators first. Oftentimes, I've had to rely on our in-house lab to create new stator compounds. The stator is the sacrificial part of a PC pump, generally wearing out 2 to 3 stators to every rotor. Buna, Viton, Theraban, natural rubber, EPDM, and urethane are some of the compounds that you'll find with PC pump companies. The reason for so many compounds is that there are a variety of operating conditions that can impact the stator, so selection is absolutely critical for success. Chemistry. Aggressive chemicals can cause an improperly selected elastomer to swell, shrink, harden, or disintegrate entirely. When dealing with aggressive chemistry, be careful to select a compatible elastomer. Temperature. High temperature will cause swelling and failure of the elastomer, stalling of the pump, or damage to electric motors from the increase in compression and resulting in high torque. For high temperature conditions, consider an even wall or even a split elastomer design that can allow for expansion. Some PC pump companies have special certifications such as FDA, 3A, even NSF for drinking water. Ask your PC pump company for options. Next, I'd like to introduce my colleague Chris Oakes, who would like to explain more about the characteristics of the progressing cavity pump. Chris?
Hello, my name is Chris Oakes. I am the Applications Engineering Manager at CPEX and have been with the company for 7 years. The municipal market has been my primary focus during my time with the company, but I've also been involved in various other industries including food, oil and gas, mining, and general industrial applications. We would like to share some information with you regarding how PC pump works, specifically the topics of slip and intake efficiency. From there, we'll move on to discuss drivetrain components and power transmission in a PC pump. So what is slip? Slip is the reverse flow of fluid in a pump and is caused by 3 main factors: discharge pressure, fluid viscosity, and fit. So as discharge or differential pressure in a PC pump increases, slip also increases. As fluid viscosity increases, slip decreases. And as fit or compression between the rotor and stator is reduced due to wear, slip also increases. From the factory, the amount of compression between the rotor and stator has been optimized. So regardless of the source of slip, we must overcome slip to have positive flow. Slip can be detrimental for a couple of reasons. First, slip can cause accelerated wear to the rotor and stator for abrasive fluids. Second, slip actually shears the fluid, which could cause damage to the product. So how do we reduce, eliminate, or compensate for slip? Well, first and foremost, a proper pump selection is key. Our goal is to optimize the pump and its components to meet the application requirements. It should be noted that slip is typically not an all or nothing situation. Some slip is okay in most situations. The most basic way to compensate for slip is to increase pump speed. By increasing pump speed, we overcome the slip and achieve the desired flow. This is actually the case for most pumps that we sell, and is completely acceptable. In situations where we want to reduce the amount of slip in the pump, we often add stages. For example, a single stage pump is rated for 6 bar or approximately 90 psi. If our application requires 80 psi, the single stage is capable, but there may be more slip than desired. So by using a 2, 3, or even a 4-stage pump for this application, we can reduce and nearly eliminate the slip. Eliminating slip and adding these stages will also extend the service life of the pump. Another method for controlling slip is to adjust the compression fit between the rotor and stator. This is less common, but it is advantageous in some situations. Reducing slip allows tighter control for metering and dosing applications. So we should now discuss intake efficiency. sometimes referred to as volumetric efficiency. This is simply a measure of how well the product flows into the pump and fills the cavities. Intake efficiency is affected by fluid viscosity and the pump speed. The thicker the product, the more difficult it is for the product to flow into the pump. Likewise, the faster the pump runs, the lower the intake efficiency. So previously you mentioned that higher viscosity reduces slip. So there's a balance between reducing or eliminating slip and having high enough intake efficiency to actually convey the product. The first method of increasing intake efficiency is to run the pump slower. This means a pump for something like peanut butter will be larger and run slower than a pump for water or other very thin fluid in order to produce the same amount of flow. If the product is very, very thick, we may never reach 100% intake efficiency, and that's okay. In most situations, we can size the pump with some intake efficiency less than 100% and compensate by simply increasing the speed of the pump. Running a little faster allows us to achieve the desired flow. For applications such as a basic transfer of material, we can get away with lower intake efficiencies because they are not near as critical as metering or dosing applications. For these applications, we want to ensure very high intake efficiency such that we have very accurate and repeatable flow rates. Another way to increase the intake efficiency is to force feed the product into the pump. What does this mean? We do this by using an auger in a hopper style pump that pushes the material into the cavities. These augers have a pitch that actually overfeeds the pump, the goal being to completely fill the cavity. Another benefit of this auger is specifically for thixotropic or shear thinning fluids is that the fluid is sheared enough to effectively reduce its apparent viscosity, making it even easier to get the product into the pump. So in summary, we should take special considerations for viscous fluids, but we do have ways of properly handling them. Next, we will move on to the drivetrain and power transmission of a PC pump. The drivetrain typically consists of a motor, gearbox, drive shaft, connecting or coupling rod, universal joints, and the rotor. The challenge in a PC pump is the rotor head rotates eccentrically, while the motor or gearbox shaft rotates concentrically. This means we need some type of universal joints to transmit the torque required to turn the pump. The closed pin joint is the most common universal joint type used due to its simple design and serviceability. It includes an elastomeric cover that seals and separates the fluid from the universal joint lubricant, which is typically a grease or an oil. Pin joints may or may not include bushings, which allow for rebuilding of the joints rather than complete component replacement. Also, proper material selection of the pins and bushings is critical for a long service life. The next type of universal joint in a PC pump is an open pin joint. The open joint is not covered by an elastomeric sleeve and relies solely on the conveyed product to lubricate its components. This is most common in the food industry, such that the pump can be properly cleaned and sanitized. Also used for sanitary applications is the flexible connecting rod, made of titanium. This design actually eliminates the universal joints altogether and relies on the flexibility of the shaft to convert concentric motion to eccentric motion. The advantage is that all moving parts are eliminated, but there are limits for speed and pressure. Also, the pump typically is longer to minimize the angularity of the flexible connecting rod. When pumps become very large in terms of flow and or pressure, the cardan type joint is used. This would be similar to that of a large truck drive shaft that has a dual pin design. Gear joints are also used by some manufacturers, but are much more complicated than pin joints in terms of assembly and serviceability. Finally, we will discuss common PC pump drive arrangements, typically consisting of a motor and gearbox. The block or close couple design is the most common, lowest cost, most compact, and easiest to assemble. The block pump components are all designed such that they easily bolt together and do not require any alignment in the field. In the block design, the gearbox output shaft bearings act as the pump bearings, so they must be sized accordingly. If the gearbox cannot be designed to handle the service conditions, a long couple pump may be required. The long coupled pump includes an integral bearing frame that is capable of handling the pump's full capacity. This design does require an external coupling, and increases the pump length, typically by 1 to 2 feet. It goes without saying the long coupled design is more expensive than the block pump, but may be warranted in certain situations.
Thank you, Chris, and thank you all for joining us today. We hope that this short presentation has given you a better understanding of PC pumps. With the ability to handle a combination of high positive and negative pressure conditions, the low pulsation and repeatable flow which saves money on chemical usage, high and low viscosity fluids are easily pumped, resisting aggressive chemistry and high temperatures, all of this while being extremely energy efficient, having less downtime, yet easy to repair when necessary. We believe this to be your best pump solution on the market today. For any questions regarding the content of this presentation, please
6.4 PC bottom hole configuration and operational management. PC bottom hole installation. A typical PC pump downhole installation is shown in Figure 65. The major features of the installation are listed here. Chop swells usually are drilled and cased 2 to 4 joints deeper than the pump sitting location to provide some buffer for the earlier massive sand influx and that occurs during startup. 7-inch casing in a 9-inch hole is standard, although some companies have experimented for years with 5.5-inch casing in a 7-inch borehole. The smaller dimension casing has not been widely adopted for several reasons. Difficulty in finding workover equipment of appropriate size, and casing distortion trapping the PC pump in the hole. A typical PC pump is a 4.25-inch OD installed on 7.4-inch or 4.5 tubing, depending on the torque magnitude expected. Early in the PC pump history, 2 7.78-inch tubing was common, but restricted flow and low torque resistance caused this approach to be abandoned for new chop swell applications. The stator is driven with a standard circuit rod string or continuous rod string operating within the tubing. Some field operators have tried elliptical rod to achieve higher torque without impeding the flow in the tubing. Special knurling sleeves and other devices are used to reduce socket rod coupling wear or tubing wear in doglegs or where the coupling contacts the tubing. The bottom of the stator is fitted with a tailpipe that serves as an inlet if the rotor extends below the bottom of the stator. It will rotate freely within the tailpipe. Various tailpipe designs have been suggested to homogenize the fluid feeding the pump intake, with little apparent advantage among different designs. A 0.5 meter long tailpipe with several 10 to 12 millimeters wide vertical slots is a common design, and a horizontal cylinder about 6 meters of metal. The tug bar is welded across the bottom of the tailpipe to serve as a firm location that can be detected when lowering the rotor, and also to catch the rotor if rod twist-off should occur, hence saving a fishing trip. The inlet of the pump, or the highest inlet port in the tailpipe, is set at least 1 meter below the lowest perforation, opening to allow some flow path in the annulus to help homogenize the pump feed. If the pump is placed higher in the hole, the lower perforations will become blocked with sand settling in the casing, rendering them ineffective in providing slurry to the wellbore, thus reducing reservoir access. A no-turn tool, or tug, arco, is installed to prevent the tubing from backing off during rod rotation. This no-turn tool was originally installed at the top of the stator in the intact casing section, but the last few years operators have placed the tug anchor at the bottom of the stator, just above the tailpipe, in order to increase the amount of gas escaping impeded up the annulus, with seemingly acceptable result. No substantial increase in well plugging. In such cases, the anchor must allow for relatively free passage of the oil sand slurry down through it to the tailpipe. 6.4.2 Surface drives. The surface drive system for PC pump consists of an electrical, mechanical drive or a hydraulic mechanical drive using a hydraulic unit that can be powered either electrical or within a HC engine, diesel natural gas. Both of these power systems turn a set of gears or large shields that are coupled to the drive rod through a clamped connection, which approach is taken depends in part on the number of wells on a single pad. If the site has one choke well and the electricity is locally available, electrical drive is lack choice. In remote locations with multiple wells on one pad, a central hydraulic power unit may be perfectible. A new development from Colac in field in 2001 is a direct surface hydraulic drive that eliminates the sheaves, belts, and gears that are used in other approaches. The new drive unit is extremely compact, only 0.3 meter in diameter and 0.6 meter long, and it is believed that it will receive wide acceptance in the industry in years to come. It requires high-pressure hydraulic oil supply from a separate prime mover. New PC pump surface drive units are equipped with automatic torque controls and computer managed optimization, including programmable shutdown criteria to avoid pump losses if pumping conditions deteriorate. PC pump operation in a new chopsware. The details of PC pump operation during startup vary from company to company, but there is a generally accepted set of practice followed in the heavy oil industry to cope with the large sand cut typical of early production in new chopsware. A few of these guidelines are listed below. During startup of new chopsware, annular fluid is usually added to allow the full system to achieve momentum. Then the annual fluid level is allowed to drop gradually, and formation fluid are produced in an increasing proportion as the input annular fluid volumes are diminished. Generally, the more viscous the oil, the slower the rotational speed. 10,000 cp oil is usually produced at 50 to 80 rpm. 500 cp oil at 200 to 250 rpm. Light oils at 300 rpm. If higher production rates are desired because the well is exceeding expectation, a larger pump is installed. During the initial startup with high sand cuts, rotational speeds are even lower because of high torque requirements. As time goes on, the tubing may be lifted and turned between 40 degree and 90 degree on a regular schedule several months to minimize to concentrate wear on the tubing. The seating depth of the rotor visa to visa, the stator is changed regularly for the same reason. In general, the annular fluid level in the well is not dropped to extremely low levels. Many field operators use values between 5 and 10 casing joints, 50 to 100 meters. But with the advent of downhole pressure gauges, field operators are tending to use lower annular fluid levels, normally 2 to 3 joints. The lower the annular fluid level, the greater the drawdown on the well, and the greater the well production capacity. However, the risk of too low level sustenance in a well that does not have a BHP gauge at the period of gas throughput will almost invariably ruin the stator elastomer. PC pump rate sand tolerance. With the developments mentioned previously, there are few constraints on PC pump rates in most particular situations. If the fluid is of low viscosity, a PC pump should be able to operate continuously at 250 to 300 rpm, achieving a displacement efficiency of above 90% indefinitely. However, PC pump performance is degraded in a number of situations, leading to practical rate limitations. During the early CHOPS period, when sand production rates are high, the viscosity limitations restrict rotor speed to values as low as 30 to 50 rpm, and PC pump are being used in deeper wells with large reservoir drawdown values. Limits of efficiency are being challenged, and keeping fluid sleep. Fluid bypassing the stator rotor seal. Low is difficulty in cases of sand production and high P values across the pump. In such cases, longer pumps with a larger number of rotor turns are used to achieve about the same P across each rotor cycle as for shallower pumps, thereby maintaining reasonable fluid sleep levels. In long inclined chops well above 30 degrees, producing fluid containing sand. Abrasion is high and speed is limited by wall friction, even with special measures. Sand setting out of the fluid in the production tubing on top of the PC pump can occur in some situations. Power shutdown, water influx. The sand settling velocity in the viscous fluid can be estimated only poorly with a Stoichiometric settlement assumption. Some of challenge arising in computing a settlement velocity include typically there is a range of sand grain size over a factor of 2 in diameter, from 100 to 200 in size, leading to a factor of 16 in different settling velocities. Larger particles settle much faster. The composition of the fluid being produced, oil, water, sand, gas, slurry, is not constant. CHOPS wells show variability in phase composition over short-time intervals. Over a period of seconds, sand content can rise from 2% to 10%, then gradually drop back to 2 to 3%. The need for online torque control is evident. The viscosity of a multiphase fluid is notoriously difficulty to measure, particularly if there is an appreciable volume fraction of gas bubbles and sand grains. During settlement of heterogeneous mixture of grains of different diameters in a long vertical tube. Grain pipe occurs, and this interferes with the settling rate of individual grains. The stocking assumption of no interaction among grains is violated. In an inclined tube with an immobile suckered rod, friction along the wall and inclined metal surface impacts settlements. In general, the actual composition of the fluid in the tubing at the time of a shutdown is not known. In many practical situations, the sand settlement velocity are slow enough and the sand concentrations low enough that it is possible to restart the PC pump even after many hours of shutdown. Sand blockage becomes more likely as the troposphere produces more and more water in the fluid. There is a widely held view in the conventional oil industry and sudden sand influx accompanies rapid water breakthrough because of the reduction of capillarity with metaphysics state changes. In tropospheres, this is not the case, but a sudden increase in water cut, and of course gas content at the same time, can rapidly increase settlement velocity so that a shutdown leads more rapidly to pump blockage and need for a workover. Finally, the major reason of premature PC pump breakdown historically apparently has been allowing the pump to operate without liquid intake, gas or air only. This problem is being eliminated with continuous BHP monitoring and will eventually become standard. PC pump and surface transfer pump progressing cavity pumps are being used more frequently as surface transfer pump for fluid that have varying amounts of solid and different fluid. These PC pumps are horizontally mounted, generally no more than 1.5 to 2 meters in length, and almost always hydraulically driven. They are used, for example, as backup slurry pumps on sand injection systems to clean out the system if a general pump failure takes place. PC pumps are not used where high volume, low pressure fluids are to be moved. Centrifugal pumps are generally used for this purpose. Similarly, high volume, high pressure pumps are almost exclusively piston and cylinder pump, triple legs or quadruplex pumps. The acceptance of PC pump as surface transfer pump speaks of their reliability under adverse conditions, such as the need to pump abrasive fluid and mixture and then have large swings in composition over a short time period. They provide easy transfer of difficulty slurries at a moderate risk and moderate pressure for long periods of time before rotors require replacement. 6.5 Sand transport and erosion. Erosion problems in tubulars and wellheads. Erosion problems are common when conventional oil or gas wells experience solid influx. In these cases, erosion can occur downhole at the casing, screen, or tubing where when sand enters perforation ports at a relatively high velocity. Higher in the hole, erosion can occur at the chokes, in the surface facility and the flow lines, and even in the circuit. Recently, new designs of wellhead and surface flow facilities have been taking place as field operators began to recognize the positive benefits of sand influx on well productivity and reliability. In heavy oil, sand erosion issues do not arise in practice for a number of interrelated reasons. The flow velocities in choke wells are generally extremely modest, so that sand grain momentum is low, compared, for example, with the high velocity that may be found in natural gas wells. The viscosity of the slurry of oil, water, sand, and gas bubbles entering the well at the depths serves to dampen any initial effects that might cause erosion at a 90-degree junction or T. The temperature is around 15 to 35 degrees for the oil produced in Canada, so there are no related high temperature effects that could aid erosion. The presence of gas bubbles in the liquid when it reaches the wellhead is sufficient to make the produced fluid highly compressible, hence less erosive. Once at the surface, the heavy oil slurry flows only as far as the stock tank, and this is generally less than 20 meters from the wellhead. Abrasion problems do develop in the production tubing because the spinning drive rod trap sand particles against the tubing wall, abrading the wall and abrading the coupling as well. Tubing life is therefore substantially shorter than in a conventional oil well, and to extend the life of a tubing string, It is rotated regularly to reduce excessive single-point wear. If the drive rods have coupling as opposed to continuous drive rods, the location of the rotor is changed regularly so that the drive rod joints do not act against a single spot on a tubing for too long. Finally, special plastic sleeves are placed along the drive rod to reduce tubing wear near joints or in zones where the curvature of the variable is substantial. Sand transport in flow lines. In addition to a lack of erosion, except for abrasive wear in the production tubing, there appear to be few incidents of flow line plugging in chops production in Canada. The reasons are similar to those that inhibit erosion. The stocking particle settling velocity is so low in viscous foamy fluid in low pressure flow lines that no density waves develop, even in wells with flow rates as low as 2 to 4 meters per day. The sand concentration is typically 2 to 6%, so that if a shutdown occurs, the chop surface facility will not plug, and any sand that settles on the bottom of a flow line is easily suspended by visco drag once flow resumes. Only when sand concentrations are above 20 to 25% are shutdowns, more common because of flow line blockage. There have, however, been wear blockage problems that have arisen in long horizontal wells in which chops was attempted. This appears to be related to the extremely slow fluid uh, velocities in the region of the toe, combined with a variable that has differences in elevation, so that sand can settle in a valley and eventually block the slow flow from the toe. This figure is a chop's wear completion. The zone around the wear is deliberately damaged to help initial sanding. This picture is a root flag beam pump. From top to the down is upper loaded bearing rubber fabric belt mast with 24-stroke soap rods, counterbalance weight, drive unit, wear hand. The rotor flex is mainly used in horizontal wells where a long stroke is desired. It is not used in chop wells. 6.3 is the geometry of a PC pump double lobe stator. The figure 6.4 is stator geometry for the modified triple lobed rotor. Yes, this is all for the topic of the chops. Before we finish this topic, I will show another video about Albert, which is the most important oil field in the Canada. Yeah, let's see the video and say goodbye.
Con Full Tigo tienes lo que quieres. Lleva un plan postpago más internet, hogar y Max incluido por un año.
It's Canada's secret weapon. Oil deposits worth trillions. But getting the crude out of the ground takes the world's biggest rigs and a mega-sized refinery in one of the harshest environments on the planet. The biggest oil companies in the world are going head-to-head in a race to build the ultimate oil sands mine. In the shadow of the Arctic Circle, 960 kilometers north of Montana, lies Alberta, Canada's massive forest. An expanse of virgin timberland the size of New York State, undisturbed for 10,000 years. Until now. At the Syncrude Oil Sands Mine, one of the world's largest feats of engineering is under construction. A $10 billion mega project that covers over 100,000 hectares of wilderness. Home to almost 12,000 workers. Masters of the biggest rigs on the planet. Hard at work in the middle of nowhere. Why are they in this remote location? Battling against one of the harshest climates on Earth. Why put up with temperatures that can swing 80 degrees between the searing heat of summer and the deep freeze of an Alberta winter? Because just below the surface of this forest lies a buried treasure potentially worth $80 trillion. It's not diamonds, it's not gold, it's oil. Up to 3 times what the Saudis have in their backyard. And big oil companies will go to any length and do just about anything, no matter what the cost in dollars or impact to the natural environment. It's a massive undertaking that requires a parade of mega machines and mega structures that scoop, haul, extract, and refine. Each element has to work in tight coordination with all the others to make a single giant organism dedicated to just one thing: to devour the sand and spit out profits.
It's hard to describe a smell other than it smells like money.
It must be an intoxicating scent, because the work is brutal. Nature has definitely stacked the deck against these guys. Because even though one of the richest oil deposits on the planet is right underfoot, it's nearly out of reach. No drill can tap it, because it's not a liquid. Instead, it's a sticky, tar-like oil called bitumen, mixed with sand to form a heavy, gritty dirt, loaded with potential, but utterly worthless in its natural form. Getting the oil, the black gold, out of this useless goop is imperative. But it's expensive. Each barrel of crude wrested from these sands costs 10 times more to produce than a barrel sucked out of the ground on a traditional oil field. Why bother? Because oil consumption has never been greater, and the price of crude keeps climbing. That's what drives these men and women to push themselves and their equipment to the breaking point. The stakes are high, but so are the potential rewards. That's why Syncrude came to these parts more than 30 years ago. Back then, the oil sands business was considered the backwater of the industry. Too expensive. But no longer. Syncrude has figured out how to make the business profitable. Their success hasn't gone unnoticed. Competitors have begun to muscle in. 35 kilometers down the road, another mega project rises from this frigid landscape. Syncrude's latest rival, Shell Oil's Albion Sands. A lyrical name for a 2,600 hectare blasted frontier of steel, concrete, shovels, trucks, mud, sand and oil. Shell Oil is the new kid on the block. And now they're playing a mean game of catch-up, building their own mega-structure. So far, Shell has sunk over $4 billion into their outfit. And now they're going head-to-head with Syncrude, trying to beat them at their own game. The winner will be the one who can produce the most oil at the lowest cost and reap the biggest profits. What's the secret? Volume. To make oil from sand, you have to move a lot of earth. 2 tons for each barrel. The best way to do that is by using the biggest and toughest equipment around. Like the old joke goes, size does matter. The whole process begins miles from the refinery, out at the vast oil sands mine. After all the trees have been stripped from the land, the digging begins.
Con Full Tigo tienes lo que quieres. Lleva un plan postpago más internet, hogar y Max incluido por un año por solo 109,900 pesos.
Con InDrive Entregas, pon el precio, elige el vehículo y escoge el repartidor según su calificación.
Every day of the year, they try to rip at least 435,000 tons of oil sand out of the ground. Falling short means falling profits. To get the job done, Syncrude invested hundreds of millions of dollars in some of the world's largest and most expensive mining machines, creating a multi-stage serpentine system for scooping up and transporting oil sands. At the head of that mighty beast, a dragline, a massive electric-powered shovel, standing almost 20 stories tall, capable of scooping 300 tons. That's like hoisting 27 fully loaded city buses in one go. It digs out canyons 50 meters deep. The dragline dumps its payload into a huge pile, food for this bucket wheel reclaimer that eats away at the mountain and transfers the rich load onto a ribbon of conveyor belts 40 kilometers long. When it's working right, one of these systems can move 6,500 tons an hour to the plant. Syncrude originally built 4 of these monster dig rigs. But things haven't gone quite as planned. Turns out that these muscular machines can be a little finicky. No match for the severe local temperatures. Under the strain of these extreme conditions, the equipment breaks down and cracks up. And And whenever any single piece fails, an entire system drops offline, slashing oil output by 25%. So even though they cost hundreds of millions of dollars, Syncrude has decided to dump all 4 of their dragline systems. This is the last working crane and bucket tandem, and its last day on the job will be year-end 2005. What could possibly replace them? Big enough to do the job, but flexible enough to prevent a costly shutdown. Without a solution to that critical problem, the Syncrude boomtown would surely go bust. Miles from the Syncrude refinery, the mine was getting by on a hope and a prayer. The massive draglines, once the pride of the operation, had proven to be its Achilles heel. So engineers made a tough call. Replace these monsters with an entire fleet of more mobile, faster shovels. They're smaller than the draglines, but at the oil sands megastructure, smaller is a relative term. Meet the largest shovel of its kind in the world. 21 meters high, that's 2 school buses stacked end on end. Packing 8,000 horsepower, this 1,300-ton excavator is capable of lifting 90 tons of sand with every scoop. 9,000 tons every hour. But that would be a pointless exercise if they couldn't get that mountain of dirt to the extraction plant for processing. For that, you need trucks. Really, really, really big trucks. The Syncrude megastructure runs on these mean machines, a fleet of 33 of the biggest trucks in the world. Tipping the scales at 250 tons, each is over 6 meters tall, the height of 3 SUVs stacked atop each other. They can tear up the gravel at speeds up to 67 kilometers per hour, kicking up a blinding dust storm. Weighing more than a 747 jumbo jet, the truck is so big that the driver barely notices as the giant electric shovel drops more than 360 tons of sand into the truck bed. Running 24/7, 365 days a year, the dump truck fleet is the lifeblood of the oil sand operation. The shovel and truck combo is a dramatic improvement over the old dragline and conveyor system. But nothing's perfect. During the spring thaw, mine roads start to soften up. It doesn't look especially muddy, but for a 250-ton dump truck with 360 tons of sand in its bed, this stuff is as treacherous as quicksand. With 1,200 loads a day moving from the mine to the plant, it's inevitable that sometime, somewhere, someone will get stuck. Like this guy. He's going nowhere fast. There's only one solution. Lighten the load and start over. 200 barrels of oil headed back to Mother Nature. A loss, but it didn't cause the mine to shut down. And even if the worst happens and the truck had become completely disabled, another can rush in to take its place. And the sand will keep on flowing, straight into the mouth of the extraction plant. The last leg of the journey begins here, at the train. That's the name that Syncrude has given to an innovative and expensive state-of-the-art transfer system. The train is composed of 3 parts. First, trucks dump their oil sands into gate-mouthed crushers that mince large chunks into bite-sized pieces. Next, the loose sands fall onto a powerful conveyor belt that transports them to a surge bin. It looks like a glorified funnel, but it is actually the heart of the transport system. It regulates the flow of sands coming into the processing plant, making sure that a consistent mix of oil, sand and rocks flows just right. Never too much, never too little. Finally, the sands coming from the surge bin are sent to a 42-meter-tall silo called the slurry prep tower, where the sands mix with water and then travel via pipeline to the main plant for processing. Since 1997, the train has run on time. A major success that engineers estimate has cut energy costs by 45%. In fact, the train has proven so valuable that the company has decided to roll the dice again. They're taking a big financial risk by building a new train. It's based on the existing system, so building it should be a breeze, right? Wrong. With a price tag of over $500 million, this mega project is as expensive and complex as a front-line battleship. And getting it built on schedule and on time has been a pitched battle. Just ask foreman Ken Notter. He's the captain in command of the building crew.
I got 2 more pieces to go on this side, 2 more that go on the west side of the structure here.
This week's problem is especially difficult. Constructing the new surge bin, the 7-story tall funnel that will regulate the flow of incoming sand. The surge bin was manufactured in Korea, then broken down and shipped here piece by piece. It took 90 flatbed trucks to haul the hundreds of massive pieces to the construction site.
These wall sections that are on the ground down here, they weigh about 40 tons each.
Ken's schedule and budget originally called for the crew to work 5-day, 10-hour shifts, but that plan went out the window long ago. They've been plagued by gale force winds that sometimes make it too dangerous for workers to scale the 24-meter tower. Ken may be worried, but like any good skipper, he refuses to show it. He wants his team of steel workers and welders to concentrate on getting the job done.
Oh yeah, guaranteed. If everything fits.
Is he joking? Sadly not. Turns out he's got an even bigger problem than weather. Some of the pieces don't quite fit. And that means mucho overtime.
Do you have it up tight now or what?
Yeah, we tried a pin, but the pin didn't help.
Well, maybe we'll get a welder up there and we could weld a dog on it and then we could jack it out.
Weld the dog onto which?
Here, I'll be up there in a bit.
Okay.
They decide that they have no choice but to try to modify the structure of one of the funnel walls. It's a tricky and dangerous job. They lift 11,000 kilograms of steel slowly, gingerly, until it's dangling high overhead, like the world's biggest guillotine. The crew slides the 12-ton puzzle piece into place. The time for brute force is over. Will it fit? A little tap, and voila! One mega milestone down, and many more to go. But other work can wait. The crew has given all they can, so Ken gives them the weekend off. Syncrude started mining in the 1970s. In those days, the price of oil was so high that it seemed a no-brainer to sink billions into a new technology to wring crude from tar. But then, in the 1980s, the bottom fell out of the oil market. The Saudis flooded the world with cheap oil, dropping the price to just $10 a barrel. Syncrude's oil cost $15 a barrel. In one stroke, their business evaporated and they nearly went under. But rather than pull up stakes and write off their investment, they decided to bide their time. And now, things are going their way. Prices are jumping again, and that's brought in the competition. Shell Oil. They've sunk billions into their own oil sand mine at Albion. Are they crazy? Didn't they learn from Syncrude's earlier brush with disaster? No one knows what the future will bring. But this time, the picture seems different. Because demand is going through the roof. The United States alone burns 20 million barrels a day, more than any other country in the world. But not for long. China, with its exploding economy, is poised to take the lead, putting ever-mounting pressure on the world to find more oil at almost any cost. Shell began construction at Albion in 1999. It took 4 years and 14,000 workers to get the operation up and working. They've pushed themselves to the limit and paid a heavy price for their ambition. This is what an oil refinery fire looks like. This blaze, filmed at a refinery in Texas, killed 15 and caused millions of dollars in damage. In January of 2003, a devastating fire consumed the brand new extraction facility at Shell's site. Work ground to a halt for 4 months. The company hemorrhaged money, while workers repaired the damage. But they got off easy. No one died. What makes oil sand mining such a perilous enterprise? Because some of the huge structures that engineers have built are like massive bombs, just waiting to go off. Figuring out how to harness all that explosive power stymied scientists for generations. But it was Dr. Carl Clark in the 1920s who developed the first method. Syncrude was one of the first to put his system to work. The heart of the whole operation is here, in the extraction facility. This is where Syncrude fine-tuned the process and became the largest oil sand producer in the world. A title Shell would dearly love to claim for itself. How does it work? Nature gave the process a head start. A microscopic view reveals that each tiny grain of sand embedded in the oil is surrounded by a thin sheath of water. Without the water, the oil and the sand would be forever bound together. But with the water, the sand is isolated and can be removed. The recipe for separating couldn't be simpler. Just add more hot water, lots of it, some caustic soda, and shake well. Every day, nearly 500,000 tons of sand mix with hot water in these 100-meter-long monster mixers called tumblers. First, the machines shake out the largest of the rocks, violently. With the big stones out and some hot water in, the mix flows into these huge basins called separation vessels. More hot water enters the mix, and as if it were the world's biggest salad dressing, the oil, globules of bitumen tar, separates and rises to the top. With a consistency of molasses, the bitumen froth empties out into collection vessels. From here, the last step is the refining process that produces the gas sold at the pump. The leftover water ends up in waste areas called tailings ponds that stretch for miles. No one is quite sure whether Alberta's forest can grow back in this hellish wasteland. But for some, there's a silver lining inside even the worst industrial mess.
Actually, we're cleaning the sand that's been spoiled by nature and put oil into it. And actually, we're cleaning up the sand and putting it back.
Cleaning the sand. That's one way to look at it. But no two ways about it. Shell's going to have to clean a lot of sand to catch up to Syncrude. To recoup the billions invested at Albion, the plant needs to produce 155,000 barrels of oil per day. Every day for the next 2 years. But Syncrude stands in their way. Because the companies are in intense competition for a key ingredient that's always in short supply. Something that neither one can do without, and must pay for no matter what the cost. Skilled workers. The job of finding and keeping good employees has fallen to Jeff Buckles.
There's just not enough tradespeople to go around for all the work that's planned and in progress up here. The other thing is the infrastructure in Fort McMurray is really being stretched to the limits.
The nearest town, Fort McMurray, is bursting at its seams. 60,000 people are crammed into what is essentially a frontier town. And it can't expand fast enough.
We can get people up from Calgary or Edmonton to come and work here, but just the fact that they can't find a place to live limits how many people we have available to work for us.
Housing prices are skyrocketing. And wages are even higher. Thanks in part to a bidding war mentality created by the competing oil companies. Rance Gillingham is a good example. He's been shoveling sand for 15 years. He used to work at Syncrude. Now he works for Shell. It's a safe bet that this top gun didn't take a pay cut when he switched sides.
The first bucket is the most critical bucket into the truck itself. Once the first bucket is in, as you can see, there is a good cushion then for dropping the second, third, and fourth buckets.
Don't let the relaxed confidence of this pro fool you. There's intense time pressure on Rance. He's got just 2 minutes to fill each truck with 4 90-ton scoops. Any longer, and he won't make the day's goal. Today he's pushing Olive extra hard, because the ground is rock solid. Rance has to crack through the 2 meters of frost on the frozen tundra. The shovel's bucket is like an ice cream scoop digging into a frozen pint of oil sand ripple. It takes a master's touch.
Once I lift the top off, then the bottom comes out that much easier. So there's a little strategy there.
But even Rance can't outmaneuver the sand forever, because the stuff he scoops isn't only frozen, it's also incredibly abrasive. The shovels dig into the sand with enough power to hoist 200 pickup trucks. The combination of extreme force and rough sand is enough to shred even the steel teeth on the front of these dinosaurs. Every 12 hours, work halts so a team of mega dentists can replace worn-out pieces of the shovel. Weighing more than 90 kilograms brand new, a single tooth can lose 27 kilograms in one 12-hour shift. Enough metal is lost into the mine every day to make 2 full-size pickups. But wear and tear is part of the cost of doing business. Just ask Colin Ashton, extraction manager. He's been working at Albion since before the extraction plant was built. Each day, Colin grapples with a daunting problem. The grit coursing through the plant's network of steel veins poses a constant threat.
We're basically processing sandpaper, and that sandpaper goes through the pipes and wears out the pipes in our vessels very quickly.
Maintenance shutdowns are a fact of life. So engineers built not 1, but 2 independent extraction lines, each capable of processing over 6,000 tons of oil sands every hour. The excess capacity should keep the plant up and running. But during the night, disaster strikes. Line number 1 goes down with a burst pipe. A At the same time, line 2 is on the verge of an even worse blowout. So Colin has to shut it down as well, putting the entire extraction plant offline. Now the pressure's on to climb into the belly of the beast, to get this line back up and running as soon as possible. Their job? Swap out damaged banana screens. Despite the fruity name, banana screens play a meaty role. They filter the slurry that jets through here, separating rocks from oil sand. But the constant bombardment rips the banana screens apart. These steel filters aren't the only weak spot on the system. The abrasive sand moves through the system on a torrent of water. The Shell plant uses 19 million litres of water an hour. And the only available source is the nearby Athabasca River. To limit their impact, Shell recycles the water they take. And that has created another maintenance nightmare for the team. They call this the Cyclopack, a half-kilometre course of pipe that fires dirty water through these 31 mini-pipes, called the cyclones. As water twists through the cyclone pipe, the waste products, sand and clay, fall to the bottom, while the lighter, cleaner water flows out the top, allowing it to return to the system. The Cyclopack, never before used in the oil sands industry, helps clean and reuse an amazing 75% of the water that the plant takes in. But just as with the banana screens, the grit in the cyclone rips the metal to shreds, often causing the whole system to shut down for damage control. There's no easy way to do it. Each time, the crew has to dismantle the beast, clean it, and put it back together again. In this cyclone, the dirty water has savaged the pipe's inner metal and rubber filter. And even more damage further down.
That's a cyclone coming out. It had to be taken out because the body's worn out from the sand going through it. It was leaking.
It doesn't take long to find the source of the leak. The waste tailings have chewed a hole straight through the thick steel skin.
Right here. That's your hole. That's what sand will do to it.
And another one bites the dust. And the chances for the replacement piece aren't much better. Most construction jobs end, but here, the building just goes on and on.
It's a constant battle, but the world needs energy.
Maintenance wizards like Colin Ashton and his team keep the plant healthy. But out on the front lines, the miners face their own troubles. The dump truck fleet struggles to operate at full capacity. Breakdowns are a constant and costly plague. Can Albion find a way to boost its immune system and keep the big rigs rolling? After 12 hours of back-breaking labour, the Albion crew has finished the extraction repairs. And not a moment too soon. Because if they don't restart the plant now, all of their work may have been for nothing. During a shutdown, the oil sand slurry sitting in the pipes and pump begins to congeal. If it's allowed to get too stiff, it could cause the system to seize up, like a massive coronary. Here in the control room, Tom Powell oversees the startup. He's like a surgeon, trying to get his patient's ticker up and running after quadruple bypass. His greatest worry is the integrity of the tailings pipe, which carries waste out of the operation. A clog here would be devastating.
We're looking for problems with pump box levels, making sure that all the pumps are operating as they should, and that we don't lose the velocity on our coarse tails line. Our tailings line is one of our lifelines to our plant. If we lose the tailings line, we have to shut down that train. That train has to go down. We'll wait.
The trick is to ease the pumps back online slowly, one at a time. But that's easier said than done, as 12,000 tons of oil sands have to be sent coursing through the plant's circulatory system. Tom's background as a coal miner didn't prepare him for the delicacy of this job.
It was hair-raising because I'm not used to the tonnages. Running 6,500 tons an hour, to me, was a half a day of running in the plant. I'm running in an hour on one train.
Slowly but surely, Tom brings the pipe back into action.
Okay, 2012 is open.
The heart of the plant begins to beat once again. Soon they're running at full capacity. But there's a new problem. The team that controls the workflow of the trucks and shovels is dealing with a major crisis.
It just got real busy real quick here.
No, I show you going to Crusher 1. You're just getting no tops.
Without warning, all computerized communications to the 20 trucks in the field suddenly go dead.
The truck drivers are not getting their assignments. We're showing the assignments, but they're not seeing it come across their screen, so they're kind of lost.
It is critical to the mine that trucks and shovels always know exactly which area of the mine to dig and process. If the trucks bring the wrong kind of sand, the extraction plant could clog, and that would be a nightmare.
Thank you. Go ahead, Willie.
So engineers scramble to get the system up and working again. Frantically, the team tries to radio the drivers to find out where they are and either give them their assignments or order them to stay put.
Okay.
Meanwhile, the spring thaw is wreaking its own havoc with the trucking fleet. Some of the rigs have been pulled offline and directed here to the mechanic shop for badly needed repairs. Daryl Osachoff is lead truck mechanic. His job is to keep the trucks in the mine and out of his shop. The pressure is on the crew to finish their work as quickly as possible.
These particular conditions are very extreme for the vehicle. It's hard on their engines, it's hard on the powertrain, hard on steering linkage.
Yesterday, Daryl and his crew made a drastic decision. Replace the entire engine. The truck has logged 16,000 hours. Daryl had hoped it could hold out a bit longer.
Ideally, we're hoping for in around 17,000 to 18,000 hours.
But this engine is cooked. A new one, weighing 18 tons, will cost $600,000. And this truck will be out of commission for the 5 days it will take mechanics to repair it.
Basically, we've taken the engine out, the torque converter, and we're changing every hose in here so that when it gets put back to work, it stays to work.
For Daryl, saying goodbye to an engine heavier and more expensive than a garage full of cars is all in a day's work.
With everything, you want it to live forever, just like our vehicles, our cars, or our kitchen appliances, right? They need to live forever in our own minds, but they never do.
Meanwhile, back in the command center, engineers think they've located the communication problem that decapitated the truck communication network. Power went down at one of the substations. Now it's just a matter of rebooting the system and the trucks can roll once more.
Yeah, you betcha.
The control room can breathe a sigh of relief.
Hello, Finning Field.
For now.
It's back up and running perfect there now, so just the way it does 99.9% of the time here.
That's why they get the big bucks. They're not the only ones. Salaries for truck drivers can reach over $100,000 Canadian. Wages are fat because labor is scarce. And that scarcity has opened doors for people who might not otherwise get a shot in a place like this. Drivers like Tyler.
I'm 19 years old and the truck's $5 million.
And Tamara. For 2 years, she's been breaking down gender stereotypes.
The coolest thing about this job is just the reaction on people's faces when I tell them I drive the biggest truck in the world.
After a few years of hard work, Shell's Albion Mine gamble is about to pay off. And they've already decided to up the stakes. Now they're planning a massive $3 billion expansion that will double output to 300,000 barrels of oil a day, putting them in the lead as the world's largest oil sands mine. But the competition isn't about to take a challenge like that lying down. In the midwinter darkness, a rumble can be heard in the distance on Highway 63. Royal Canadian Mounted Police have shut down traffic in both directions to make way for a massive new addition to Syncrude's processing megastructure. At 60 meters long and over 360 tons, 2 trucks have to team up to tow this one piece. It takes several days to drive it 435 kilometers from Edmonton. And this is just one of thousands of gigantic new parts arriving here by truck.
Con Full Tigo tienes lo que quieres. Lleva un plan postpago más internet, hogar y Max incluido por un año por solo 109,900 pesos.
Con InDrive Entregas, pon el precio, elige el vehículo y escoge el repartidor según su calificación.
An isolated outpost, like the Timbuktu of the north. It is through these enormous vessels and pipes that the tar-like bitumen flows and is transformed into lighter crude oil, in the final stage of processing called upgrading. Already larger than Manhattan Island, Syncrude is expanding its upgrading facility in one of the largest construction projects on the planet. If they succeed, they will double their oil production to 500,000 barrels every day. Take that, Albion. There's just one problem. They've run out of room. So the only option is to build up instead of out. 90 meters up. And that complicates matters for the team that's in charge of constructing the centerpiece of the new expansion project. This may look like a deadly missile, but it's not. It's a 540-ton segment of the plant's brand new coker. A coker is the cooker that refines the heavy tar into a lighter, sweeter, and more valuable product. Inside, temperatures soar above 500 degrees. Sprayed under high pressure into the coker, the bitumen flash evaporates, creating a lighter oil vapor. The vapor rises and eventually condenses into the final product. Leftover carbon residue, called coke, makes the way to the coker's furnace, where it's recycled as fuel. The new 85-meter tall coker has to fit snugly into the old upgrading facility. Irv Parson has the job of orchestrating the work. And between the tight confines of the construction site and the complexity of the system he's building, he's got his hands full.
We're a year behind or so we'll never be on schedule, but the things are getting done now.
He and his crack team slowly hoist the steel, as heavy as 80 elephants. And by day's end, they manage to slide the new coker right into place. The hard part will be hooking it up and bringing it online. For that, they're going to have to get their men into position, high overhead. And that puts the burden on the shoulders of these guys, the scaffolders, the daredevils of the job site. Their job is to forge a path to the hard-to-reach places that the pipe fitters and other technicians have to get to.
The scaffolding becomes an inherent part of trying to build these places now. Once upon a time, it was considered an accessory, and now you can't build a place like this here without temporary scaffolding.
Today, scaffold foreman Kathy Kitty Cat Bouchard leads her team hard at work 60 meters overhead. They're preparing the way for the final installation of a vital new piece of equipment. Something that won't add to Syncrude's bottom line, but will reduce pollution. This is the best in sulfur dioxide reduction technology. In its natural form, the tar-like bitumen is heavily contaminated with sulfur. Burning it releases the sulfur into the air. Getting the sulfur out before shipping the oil is critical. Some of the sulfur comes out of the bitumen in a molten form that eventually solidifies and ends up here, piled up to form these growing pyramids. 4.5 million tons so far, and growing by 1,500 tons a day. Syncrude's cokers release 227 tons of sulfur dioxide gas into the atmosphere every day, a dangerous pollutant that causes acid rain and smog. That's where the new sulfur dioxide reducer comes in, and the scaffolders. They lock aluminum beams together with clamps to build this temporary walkway 60 meters above concrete.
I'm not afraid of heights, but I really respect it. I'm always careful, I always tie off, and I'm always watching my footing, and I never take for granted that nothing's going to happen to me. Just watch your step right here.
They knock the last clamp in. Right on time. A job well done. Welders will follow to make the final connections that will bring this baby online. It's taken 4 years to get this far in the construction of the new coker. Thousands of tasks still lie ahead. Pipe fitting, insulating, electrical work. At least another year before anyone is calling this job done. But even this is only the beginning. In the continuing quest to cut costs and increase profits, a mega project like this has to keep moving forward or die. Within the next 30 years, there will be more mines like this, transforming this frozen forest into the Saudi Arabia of the West. It won't be cheap oil, but it could be a steady supply, with reserves equal to the amount of oil consumed worldwide for 55 years. But extracting that energy is already having an unprecedented impact on the Canadian environment. Trees cut, water diverted, air and soil polluted. The oil industry has promised to restore the wilderness after the mines are no longer active. But no one knows how long that will take, or even if it's possible. For now, though, that seems a risk that the world is willing to take.